Yeah. Okay, we can start maybe. Should we? Okay. 3, 2, 1. So, hello and welcome everyone to the third day. Is that true? The third day of the summer deep learning bootcamp of LauzHack, which is, I think the first time was last July. Then we had another one earlier in the winter this year, and then we have the third one in summer. Today, the topic is about recurrent networks. So after what we learned about earlier versions that we saw in the past 2 weeks of neural networks and then the CNNs, I assume, we now go into recurrent neural networks. We will see together basic concepts, several variations, several tasks that we can do with these networks. And finally, we will also code a bit to see in action how we can use them in practice. And in the end, we will also see a specific example of all of the methods that we will see today in the domain of natural language processing and text. So with that said, let's get started with a quick recap of what we had in the past 2 weeks, and then let's get on what is new. So you started, again, in the beginning, I always say a lot of things might be boring to those of you that already know this model. This always happens when we have such bootcamps, but there are also some people online and some people will watch the videos. So we have to explain everything from scratch. So if things are boring for you, sorry, because we need to usually cater to everyone in the audience. We have started from, and also I will try to keep the time not too long so that it's not like the past 2 days because there are more basic topics. I see someone laughing in the audience. So for that not to happen, we'll try to also keep it short because we'll have 2 sessions. One is also tomorrow, which is basically a kind of continuing of today. So let's dive in after all of the admin things that I have to say. In the past 2 days, we saw basically deep neural networks. What were deep neural networks? We had some input data here that you can show them as a vector, or basically as a kind of representation that can be identified as a certain number of numbers. You pass it to the input layer, and then you have several layers. Each layer consists of certain cells that we call neurons. Neurons are basically a linear function of the input to the neuron given to an activation function, as you already saw. For example, here is a neuron. These were several inputs. They were combined together in a linear way, and then we applied an activation function, for example, tangent hyperbolic, or like, I don't know, sigmoid or whatever function here, and then it gives a value and output. What we saw in the deep learning revolution was that if we connect certain number of these neurons together in the form of different layers, like here we have a hidden layer 1, which consists of 4 neurons, and another hidden layer 2. If we combine them together sequentially, what we saw was that after training the model, we will have a model that can predict a certain value in the output from the input values and can generalize on a lot of tasks. I assume you have seen examples with maybe tabular data. I don't know what examples have been exactly covered this year, but I don't know, with tabular data, for example, you want to predict the prices of housing. You give all of the input features, we call them features, all of the features to the input, and then the price would be the dependent variable, which is in the output. And then this model is trained to predict the prices from the features based on increasing and decreasing different weights of the different hidden layers. By weight, we refer to the weight of each of the inputs to each neuron, and then you usually basically make a linear function out of them by multiplying by different weights, and then you also add a bias, and then you get the output. So these are the basic things. Sorry, I had to go over them because that was the classic thing that we always do. We also saw that there is a process called backpropagation to help the model learn the weights so that it can generate the output from the input. You basically have a lot of inputs and a lot of outputs, which is our data set. And then whenever you see one output, you change the weights of the model in a way that the output can predict the inputs better. In the backpropagation process, we won't go over the details, but I think you have been over them, so you already know. But what backpropagation process does is that it predicts a better output after seeing a lot of different inputs over the time of data set. So we assume that with more data, normally we will have better models because it can do the backpropagation more and it can update the weights such that it fits the data more. So that was what we saw from deep neural networks. You may have also seen certain concepts such as overfitting. I assume you have seen it. If not, tell me. Basically, what overfitting was that imagine we don't have, for example, a lot of data that can express what the model should predict, but we train the model a lot on that small set of data. What would happen is that the backpropagation process would lead to the model basically memorizing the input and setting the weights in such a way that it knows if I see this input, I should give that output. That's not good, because the model would only work with the data that it has seen, and it won't generalize well to the new tasks. So it's better to not to overtrain the data, or as we call overfit the data, overfit the model on the data that we have. I talked a lot, sorry. So then we saw convolutional neural networks. We saw that, okay, neural networks are good for a lot of tasks. Actually, in theory, neural networks, just a normal deep neural network, can model every function. In theory, you can prove that it can model every function in the world if you just add the layers and the output. But is it efficient? Can we do every kind of task deep learning in the world with just these models? Otherwise, we would have just ended the bootcamp in the first day, right? We can't. There are several cases in which we can add new things to this whole paradigm. Still, we will have some neural network there, but we can add features. We can do something before. We can do something after. We can change the architecture of the model and so on, in a way that it helps us do tasks that are normally difficult with a deep neural network. One example is a kind of task that need image. For example, we want to classify image. You have a data set of images of cats and dogs, and we want to see which one is a cat, which one is a dog. What we will do in the paradigm of CNN is that, okay, we have our input images. A still image is a kind of file, so we can show them as numbers. We pass them through convolutional layers and pooling layers, as you saw the whole process. And this acts on as the feature extraction. By feature extraction, we mean a helping module to your current architecture that would help the final deep neural network to get a better input signal. Because if that network is basically simple, right? It's just a backpropagation on input mapped to output. If we help the model to get a more valid input, it can train better and it can generalize better. That's what we will also see today with text. We'll also see, not with CNN, but we'll also have another earlier module that we do some kind of feature extraction, some kind of transformation on the data before giving it to the final fully connected layer, to the final deep neural network. So here, these layers, the convolutional and pooling, they don't do the classification. The classification is ultimately done by the deep neural network that is over there. What these layers do is that they transfer the original image to a set of feature inputs that the model can train on them easily. You might here ask, why do we do this? Why don't we do another transformation on images? Is there any kind of proof, like those mathematical proofs that we can prove, yeah, this doing of convolutional then pooling is good? The answer, unfortunately, mostly is no. There is usually not such proof. Like proving techniques, it's mostly like people experimenting with different kinds of things and hoping that it will work, and then running, and then so it works. A lot of things in machine learning and deep learning have been discovered like that, unfortunately. So we can't prove that, yes, for an image, we definitely need to do convolution, we definitely need to do pooling and so on. That's not true. But okay, in practice, people saw that CNN is good. They are pretty easy to implement. So people have been implementing it since a long time ago, and they have been used a lot. Yeah, that's it. So again, we do feature extraction and then do the classification. I think enough talk for revision. Let's jump into a new task. Today, we want to introduce a new task that have not been supported by deep neural networks and convolutional neural networks. We're supported, but not necessarily. And that is time series. What do we mean by time series? If you don't know, any kind of data that we can measure at regular intervals or step by step is considered a time series. For example, you are building an app for predicting weather, and you record the hourly temperature in a city. Like in 9 p.m. is this, 10 p.m. is this, and so on. It's a kind of data measured in regular intervals, which is considered a time series. Heights of ocean tides, heartbeats per minute, like if you're making a health app, stock prices of companies. In the domain of education can be answers of students to exam questions. This is also interval, right? Because you answer questions one by one, so each of them can be considered a time. So it's also a time series. Or even, this one may be a bit unintuitive at the first time, a written text. Why do we consider text as time series? Is interesting. Because, yeah, if you just consider a sentence, I like EPFL, You can consider that the word I was the first step, the word like was the second, and the word EPFL was the third. So in a sense, it's also a time series, but here time is not used at its normal definition. Time is used to mean a step, and that's fine. We don't mean necessarily time by seconds and minutes, but as steps. And we also call it a time series. A tip to know if a data is time series or no is that if semantics of the data change by permutation, it's a time series. For example, in the task of predicting prices of a house, given the area of the house, the features of the house, and these kind of things, it doesn't matter the order. If I first give you the area of the house and then the features that the house has, it's not different than if I first give the features of the house and then I give you the area. But here, of course, heartbeats per minute, if you're doing an exercise, it would increase over time, right? So if you just permute the data, data semantics change. The meaning of data changes. And also in text, I like EPFL is different from EPFL I like. The second sentence is a normal sentence that a sane person would say. The first sentence is like, who are you saying this? You're saying, you're talking weirdly. EPFL I like. So it means that the meaning of the data changes. So this is also a time series task. You can always show time series as a plot against time. So basically time is the independent variable and the dependent variable changes over time. All fine? You have any questions here? All fine? I think it was simple. So, but otherwise, let me know. Good. So if classifying, I should also say here, we can do two tasks with time series. We can either classify a time series or forecast. What do we mean? By classify, I mean that I will give you a time series and you will tell me which class that time series is from. For example, I give you a plot of heartbeats per minute of a patient and you tell me if this patient is sick or not. I will give you an hourly temperature in a city and then you will predict if it is likely gonna rain or no. I will give you a written text and you tell me, is this sentence a positive emotion sentence or a negative emotion sentence? This is classification. You can also do forecasting. By forecasting means I will give you the time series until one point, and then you should predict the next point. In hourly temperature is exactly the weather forecast app. I have all of the temperatures of the past couple of hours, and I will predict the next temperature. Or height of ocean tides as well. Or I have answers of students to questions in an online platform, step by step, and I will predict the next. Or in a written text, someone has typed in their keyboard I like, and then I will suggest the next word as an autocomplete on what they should write. So they do the forecasting, right? So the task that we have here are either classification or forecasting. Any questions? Fine. Good. So is classifying or forecasting time series data obvious? You can say that, okay, yeah, it's obvious because we can just give it just as a time series here, right? Just give each time series to one of the inputs, feature one, feature two, and then let the model do its task. But in reality, the model needs to, we should somehow intuitively help the model in this process. Like images that we had to help the model by doing the convolutional stuff, here we also need to somehow help the model to be able to easier extract trends, extract cycles, rises and falls, and all of that. We have all of this in time series data. We have trends, we have cycles. In weather, every morning, every night is usually colder than the day, so we have cycles. We have rises and falls in the data. The data is continuous in time series, right? In a sense. So we should somehow help the models. And now let's see what is the problem of normal neural networks when they deal with time series data. They don't have memory. What do we mean? Each input entry in a neural network is processed independently. Basically, to be able to give our data, the whole sequence to the model, which we can see an example of a model there, we should do flattening. By flattening, we mean that we convert the whole time series into one big vector, and then we can give it into the input of the model, right? This is not very good, as shown in practice, because if you do time series data with basic traditional neural networks, it doesn't work very well. The intuition could be that time series data comes gradually. Flattening does not make much sense because also in this network, it doesn't matter if we give an example over there or here or here. All of them are passed to the next layer with just different weights. So the model does not identify, oh, that's my first neuron, this is my second neuron, and so on. And also, what researchers found intuitively is that it's better if we have an internal state that changes over time and is constantly updated, that calls the memory. What do we mean by memory? Imagine a time series comes and you want to have a model that would predict it. An idea that early researchers had was that, okay, let's have a kind of neuron that updates its memory whenever it sees a new time series data. So that the neuron does not only pay attention to the inputs, but also to everything that happened before, because its memory has changed. It's similar intuitively to how humans work. We don't see the whole time series in one step when we are living a normal life, but we see it over time and our memory gets updated. So whenever we see a new data point, we use all of the memory that was updated over time. We usually call it an internal state. That's a verb we usually use to refer to the memory.
So
yes,
the internal state is a memory in the end.
Yeah, so those are all metaphors, right? We really don't have a memory inside the neural network. You will see how we simulate having a memory. But it's all metaphors that we use for referring to this. When we say memory, when we say internal state, we mean something that would change inside an architecture. We do something in the architecture so that it can apply to time series. Yeah, I mean, you will see examples, so it should be fine. Yes. Okay, with that said, we will see an early example of a model that had memory in a sense. And let's see how it works. Recurrent neural networks. In a recurrent neural network, again, we have our input layers. Here it's shown as one circle, but you can consider as input layer. And we have an output layer, and we have a hidden layer. However, we also have something we call a recurrent. The output of the hidden layer in the middle is used as another input in the next step. This is a kind of feedback loop that you have in a lot of different systems. And by this, we ensure that every time an input is coming, of course, it's processed by the hidden layer, it gives an output, and that output is used again the next time that a new input comes, so that the model knows not only the current input, but also the previous input. Not the exact previous input, but a transformation of the previous input. Data here, input, data come here, it does some transformation back here in the next step, so that when we go over the steps, the value that has been in recurrence there has been the internal state that has been updated by every other step. This is the basic architecture. Now let's see it more in action to see what it looks like. This is a simple RNN. We unroll it over time. So basically, RNN is like a recurrence thing. We unroll it over time so that we can see in practice how it exactly will work. Imagine we are at time t minus 1. T could be 1, so we can be at time 0. This is like the first time that we are. We have a cell. And input t, we also have a cell, t plus 1. In each of them, I just unrolled it over time so that we can see it over time. Let's consider the current time. Imagine we are in second t. We have our input that is come in second t, like the current input of the time step t that goes into our recurrent network. But this is not the only input. We also have an input, which is the output of the cell in the previous time step. As you can see here, we call it a state, because it's updated over time. A state was actually connected to the output. So if we stop at time t minus 1, the output of our model would be what we are giving to the state at time step t, right? So we are giving 2 inputs to the cell at each time. Not only one input, but also a state. And then the cell also gives us an output. And then again, that output is used as the state of the step t plus 1, and this continues forever until we reach the end of the time, end of our time series, in which we just discard the last output. And basically don't discard it, but we just have it as our output, and then we don't pass it as a state again. How do we calculate the output? Because in a normal neural network, we only have one input, right? How do we calculate the output? So we have still this part, like this row and this row, WO times input T plus B of O is what we had in a normal neural network, if you remember as well. It was a linear transformation of the inputs. linear transformation of the input plus the bias, right? We also already added. Now we add another one, a U of O times the state of t. Basically, now it's like two linear transformations, one on the vector of input, the other on the vector of state, and with the bias, and then we pass it to an activation function, which can be a tangent hyperbolic, which can be the sigmoid or whatever, right? And then that would be our output, which is used as the next state. Any questions? We're fine? Yes.
So what is how do we define it? C minus one, C whatever. I mean, where do they come from?
Yeah. So these are the inputs of our time series. Imagine we have a time series, heartbeat per minute, and we want to predict, and we want to train on the data to predict heartbeats, right? Imagine we have 5 per minute, and we collect every second. So we have 60 data points. It will be input 1, input 2, input 3, up to input 60.
So in terms of the layer, would it be in the so we input all of them one by one in the layer?
Yes, in a sense. So basically, what the model does here is that it wants to, okay, the model does backpropagation, right? So for example, you can define that, okay, I will give the input until now, and then it should give me the output with a certain window size. We will see a specific example of how it works. But for example, imagine the case of heartbeat. 1 minute. You want to predict the heartbeat after, for example, you want to make an app that will predict your heartbeat after a certain number of heartbeats. You define a window size of 10. You give the first 10 inputs, and then you do the backpropagation of the whole network in a way that your output would be the 11th heartbeat. Then you do it again. You pass heartbeat 2 to 11 and ask it to predict the 12th heartbeat or things like this. So basically move the window, slide the window over your time series, and at each time you give, for example, 10 inputs here, and then you ask for an output. We say the word one by one, but in practice, what it means that it's basically a big neural network, right? It's a lot of different states that are connected to each other. What you mean by one is that this state comes from this one, but still you have the whole architecture and you pass the inputs here. Yes.
So in chat there are 2 questions.
Yes.
One is why output T saves information about previous input.
Okay. Maybe let's try this one first.
The second one is
Yes.
UO. Is it another trainable data? But I guess is it another trainable weight?
Yes. Yes. Yeah, U is a trainable weight. It's just in the background. Fine. What about the other one? So output T depends on input T and state T. And state T was also output T minus 1, which itself depended on input T minus 1. So indirectly, output T also depends on input T minus 1. And if you continue this process, each output depends on all of the inputs in prior. That's what we want also in time series. Yes.
How do you deal with the first step, which we have no prior?
Oh, yeah, that's a good thing. So ultimately, when you want to use an RNN in practice, we have some data that you want to predict from, right? For example, if you want to predict your heartbeat after, like, if you have like predict your heartbeat, in reality, we don't predict heartbeat randomly, because imagine, okay, that's a good one. So imagine we are training a model that would predict your heartbeat after 5 seconds. If you deploy it in a real world on a real human, it would not make sense to predict heartbeat from nothing because you have no data about the human, right? So in practice, you collect their heartbeat for 5 times, and then from there you start predicting. So did I explain it well? Maybe I can explain it again. So do we have more? So imagine we have, these are the heartbeats that the user have, and we want to predict this one. Yes. Yes, but where is the camera actually?
So it ends almost where the table ends. The table you left.
Right now?
Yeah, you can a bit to the right.
Like this?
No.
I can see where you are at first.
Ah, I see there. Okay, but it's not very clear.
It's fine.
Okay. So we have 5 time series. We have in our time series, we have 5 heartbeats, and we want to predict this one. Then we have a big data set, right? We have a big data set. Data set could be like, I don't know, 10 million heartbeats. But we do windows, so that we can predict in a certain format. We have 5 of them and predict the next one, right? Then imagine you want to move this model to production, to a real world app that would predict your heartbeat after 5 tries or whatever, like to a real smartwatch app or whatever. Still, you can't use this model to predict only your heartbeat after 1 step. That's not possible because the model is trained to see 5 input and then achieve the raw output. It has updated its weight to do that. You can't do it like this. So in reality, you can't predict data without seeing prior data. But this is another problem in practice because also if you want to have an app that would predict heartbeat, you want an app that would predict heartbeat, not to guess heartbeat. So in reality, you will also collect 5 data points from your user and then use your model to predict the 6th one. Also in weather, you collect, if you go to a new city, you collect the temperature for like 5 hours and then you predict for the next one. It's always the same. There are methods and ways to overcome when you have less data points. For example, you can train on a mixture. You can train on, we will see actually in Transformers lecture, I think, in more details, but you can always train on a mixture to make sure that the model basically works even if you have less number of points. For example, you can do 1 prediction at a time, which you will see, I think, an example tomorrow or even today, but that's generally the thing. Yes. Was it clear?
Yeah, like training-wise, how to initialize the sequence, right?
That's the thing. You have the sequence from data. You are training on your data set, right?
Yeah, but I need an output of the model, right?
Yeah, you always need an output of the model. So you have if you have like this, you do the windowing. Like imagine I have 1.6, 7, 8, 9, 10, and you want to predict 5. The first 5 that you choose is this.
Okay, let's phrase it this way. If the model starts, it has to give like the first output, right?
Yes.
And to make the first output, it needs a prior output.
Oh, you mean here? You mean what's the initial state?
Yeah.
Oh, the initial state, you can initialize it to whatever you want. It's fine. The model would learn the weight in a way that usually, I think people set it to random numbers or 0 or whatever. I thought you're talking about the real world production. I'm sorry. If you what is a state 0? A state 0 could be, you can initialize it to a random value. It's fine. The model would learn the weights in order to fix it. Yes. Yeah, you can initialize the random value. Yes.
Questions from Zoom. So the output depends on previous outputs, and that's why the output is acting like a memory. Is it correct?
Yes, because what acts like a memory is that the state that is updated over time, right? And the state is basically as the output of the previous step. So if you remember like this, yes.
Yeah, is there a tuning parameter which lets us control the way you all are updated? Suppose we want the recent data to be more important than the old data.
Yes, we will see examples of this in LSTMs later. Yeah.
Can we say that these networks function like finite state machines?
I mean, that's an abstraction, right? I mean, you can say always because, like, I mean, it's. I don't know if people make this analogy actually commonly. Do they?
I would say that there are finite states.
Yeah, I would be careful with saying that. I mean, it's an analogy. We don't need to make that analogy for this model to work also. So yeah, I would say. Yeah. Okay. Yes.
So how many weight matrices at the end will we train? Like, I mean, my question, my doubt arises from like the box, the box that we have.
The box is a neuron, basically, in a sense.
But they're like stacked. They have like some kind of hidden weight matrices that.
Yes, they have the weight and bias there.
And are they? So if you feed, so I'm thinking of this like thing as a channel, and then like you have a box, and this box has some weights. So if you feed again, so at the end, this box has like the weight that universally trained such that. So
Yeah. So in the end, yes, exactly. In the end, the weights are trained in such a way that it would predict the final output of the model as the true output that we want, because we do the backpropagation process. You see, so the model is not trained to exactly generate what output at each step. We only care about the final output usually. I mean, in this kind of prediction task. So we basically, you can also do some other things with other outputs. We'll see examples also tomorrow, but the idea is that you train the weights. Imagine this as a very big neural network. You do the backpropagation on the whole network in order to find weights that will, from the inputs, give us the final output. We are just trying a different way of constructing the network. The whole backpropagation process still exists, and we don't change it.
So the follow-up is that does it mean that after its training, for example, we let T, we let our data set, like big T, would be like whatever, and then does it mean that when after its training for each input at state that I have, this will give us the correct output, like for each.
It's not for each state. You for the whole window of the time series. Like for example, here for this, you train it once and adjust the weights. For this window, you also train it once and adjust the weights. For this window, you also adjust the weights and so on.
But what
Yeah.
about like after training all of
After training all of this,
to this later time, will it still work in the early time?
yes. The idea is that the model, and also you don't do only one time series, but also a lot of time series, like heartbeats of different people. And the idea is that after doing all of this, the model should be able to recognize patterns that are common in the data. After doing it, I think that's what we expect the model to do. Yeah. Yeah. Yes, or maybe first you answer that.
So in the chat, one question is why do we need output T-1, output T-2, etc.
Okay.
For forecasting, we only need the last.
For a state, definitely we need it. And there are also cases that we will see, I think maybe later or tomorrow, that we can also use the output of other cells, not only the last output, but we'll see it later. Yeah.
The second question is people, not everyone understood why we need recurring neural networks, like what is the benefit? And is the only point is to save order of the elements, like how recursion helps with the order.
The idea is that here, output T depends on input T-1, but output T-1 does not depend on input T. Because we are going over time and the state is only going one way and not the other way, the time series step only depend on what that came before them. And that's important because in a real world prediction, we never pay attention to what would happen in the future. Always the things that determine the current state are the things that are happening in the past. Like this is the common pattern of the data, right? If we are like plotting something like this, we only care about what happened in the past to be able to predict the future, not vice versa. So that's the reason that output T-1 does not depend on input T, but output T depends on input T-1. And that makes the whole process that why we need this RNN sequential thing to happen. Yeah. Yes.
So for solving this task, like predicting the R bit from the last 5 samples, is it possible to kind of, instead of using a recurring neural network, just using a non-recurring neural network and giving the sequence of the last 5 samples?
Yes, of course. I mean, basically, you can't, in theory, do anything that you can do in deep learning with a normal neural network. And also, in theory, it has been proved that neural networks can model every function in the world, basically every function with certain characteristics, right? But in reality, it's similar to CNNs. You can also flatten an image and give it to the neural network and ask it to predict. And maybe for simpler images, it will also work. But always the kind of changes that you do in the model are the empirical changes that researchers did without any proof behind them, saw that it worked, so they just continued using it. People saw that using RNNs would help in time series that compared to normal neural networks in many of the tasks. So that was one of the reasons that these models got popular. It was just because they tried and they saw it. In practice, it works better. Maybe it's not a mathematical proof behind it, but in practice, it works better. Yes.
Chat asks you to re-explain the window analogy.
Okay. So I wish I had something on the slide, but yeah. So imagine we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, so high? Okay. Maybe I can redraw here. Is it okay here?
Yeah.
So imagine we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a data set. This is one time series, right? Recorded in 10 timestamps. Imagine these are heartbeats of a user. and we want to predict a heartbeat given the previous 4 heartbeats, for example. We should do windowing like this. For example, this is one window. There are 5 of them. We give, for example, first 4 to the model and predict the 5th one. Then we move it 1 step forward. We give these 4 to the model and predict the 5th one. Then again 1 step. We give these 4 to the model and predict the 5th one, and so on. By this way, we ensure that always the model sees a certain amount of window size, so that it knows that the model learned how to predict heartbeat given the previous 5 heartbeats. That's the way that it goes. We will also see a code example of all of this, by the way. I have also an example that we'll go over together, and we'll see the code, so no worries about that, but yeah. So, right? Good.
There is another question. So,
Yes.
is it possible to account for statistical violation while data collection ensures that the RNN predictions wouldn't be biased?
Huh? Statistical, what's that?
I'm not sure what biased the word was. Or what. Well, let me ask in the chat.
Yeah, this was next level question. Okay. So with that said, let's maybe go a bit forward. We'll see in code later. I think I'll move the code to the end, so we'll see it. But okay, what we saw was that RNNs include a hidden or memory state that is updated over time, which remembers information about sequences. Researchers in practice found that it gives us better sequence matching, which is useful for time series data. And also we saw that textual data is a good example of time series data because text is something that also happens step by step. A question that you might have here is that how can we make, for example, an autocomplete system using it? Now I think it's pretty simple to us. If you do the windowing analogy again, imagine I want to write a system that would autocomplete text for me. I love attending summer bootcamp. We can have, for example, a window of 2 that will predict the next one. Actually, it will be a window of 3, basically, right? So, for example, I will give you I love, and then the model would predict attend. Then I have another one. Love and attend, the next one would be summer, right? And so on. Okay, you might think that it's not very good because only 2 examples and not very good autocomplete model. That's true. There are a lot of better ways that we can do autocomplete that we'll also see today, tomorrow, and next week. But this is one way to do that, right? If we consider time series, consider text sentences as a time series, we can always do this kind of thing that we will have a 2 tokens or 2 words basically in 2 steps, and then we will predict the next one. So we can move the window and then continue the task of prediction. Yes.
Yeah, so the question was something like this: like imagine you're predicting the temperature, and for the several days you have exactly the same temperature each day. How to ensure that RNN would not always generate the same temperature?
I mean, it would generate, so we need more data for that.
Yeah, if
It would overfit to that data if the data is like that.
so if it's like that, it won't.
Yeah, I mean, because if you have the data that is like always like very weak signals, it would just train on those weak signals, right? The model cannot generalize above what it says in the training data normally. So it would learn not actually. Yeah, I think if you that's one of the reasons that actually good data is important, right? Previously, when you trained also these models on like textual data, they generated very horrible text. But now, basically, the new GPT models and all of these, they do a lot of work on making data processed in a good way, like a very good textual data that basically you can predict well from it. So they clean up the data, they make sure there is not repetitive data, there is not wrong signals, so that the model can learn better from it. I think there's no way that if the data is such bad, and all of the data samples are like that, which is unlikely, then the model doesn't learn anything new, basically. Yes.
The window size hyperparameter that we include.
Yes, you can actually. When you also we'll also see later, there are ways that you can have actually even variable window sizes over time. Like there are models that you can only give 1 or 2 or 3 or 4, and in each case it will work. We'll see examples of that, but later. But normally, in a very simple way that we'll also see today, is just define a fixed window size, and then we use that to predict. Or you can always have also variable. You can train the model so that it sees 1 and then tries to predict the next, also 2, also 3. But then for that, you need more data for it to generalize well and all of that. The simplest case is that you have a fixed window size, yes. That's a simple way, basically. Yes.
How does the RNN know that it predicted the full text and needs to predict the new set of stuff? How to understand that there is a dot?
There is a dot. What do you mean? It's not predicting a sentence. It's not predicting word by word. That's what I described.
Yeah. So basically, the question is about start and then talking.
Yes. So the thing is, yeah, there, specifically when it comes to text, there are unique things that we do. It's not that exactly we just convert text to number. We will see some of them, I think, today, and maybe some of them tomorrow, and maybe some of them next week, the NLP lecture that another PhD is going to present. So yeah, text has its own set of things that we need to do before making RNNs work. Actually, nowadays, no one else uses RNN for text. They are a bit old school. There are newer models that we'll also see some examples tomorrow that people use. But this is what it started with all. So we are going from the basics so that we can transfer. Yeah, as you can see here, there's also basically another example of an RNN shown in a different way. This is a conceptual way. This is not exactly how it's calculated. Conceptually, we have an output and a state. And normally, a state is the same as output. But we'll see an example that a state can be different from output. We'll see soon. For now, just imagine it's the case. And then we have in each cell, we have basically the values. And then they get the input and the state, like input at each time. We see t equals 2, t equals 3, up to t equals n. And then we get a set of outputs. We can always show an RNN in the compressed format. This is the compressed format. We have the input, we have the final output, basically, and then we have this recurrence. Basically, if you roll it over time, it would be like that. And this is also the mathematical formulation of that. So we have, at each time, we have, here it shows with a different number. Instead of u, it uses w of h and w of x. It's basically the same thing. So it's a linear combination of the input and a linear combination of the previous state. Here they call it state H, because the hidden state, H is for hidden. Then you combine them together by summing them, right? It's a weighted sum, basically, because WH and WX are basically the coefficients here. Then you give it to the tangent hyperbolic, and then you have the hidden state. Here, what in this example do is that they have a different hidden state than the output. They again put the whole thing in another linear layer and then apply softmax to get the output. You don't necessarily need to do this because you don't necessarily need prediction at each time. But if you have the final RNN, as we described here, the final output that you get can be any number. We usually want it to be between 0 and 1 because we want to predict, for example, a certain quantity if it belongs to a certain class or no. For example, we have the heartbeats. If you want to, for example, predict if the patient is sick or no, we want the probability. So we always pass the final output in a sigmoid or function that would keep the values between 0 and 1. This is not always necessary. In this example that you want to predict next heartbeat, you don't actually need a sigmoid. Because you want to predict a number that could be, my heartbeat could be 90 or 100, right? If I'm doing exercise, it could be 120 or whatever. But you want to predict if you're sick or no, this is a probability. So we need to pass the final output to a sigmoid layer. That's basically what it means here. So it's nothing. Softmax is basically a version of sigmoid for more than 1D data that we will also see later. I think tomorrow we will see exact formulation of how it is. Any questions? Did you get it? So basically the difference is that when you want to do probabilities, you also add a sigmoid in the end to make sure the values are within 0 and 1, because the sigmoid function is like this, right? Sigmoid function always keeps the value between 0 and 1. Whatever you give to the sigmoid, it will give you an output between 0 and 1. Oh, this is very bad. Yeah. Okay, never mind. There is a problem with RNNs. What if the pattern continues? Imagine we continue this RNN over time. We increase the window size. Why do we need to increase the window size? In some tasks, a window size of 5 is not good. Imagine you want to make it for text and you want to write a story. You want to give it a whole book and ask it to continue writing the story. What ChatGPT can do. How many windows would be it? The window size would be so big, right? If you consider each word as a window size, it could be window size of 50,000 or whatever. In many tasks, window size of 5 does not make sense. However, you can just say, okay, we increase the window size and we train the model, we call it a day, well, we won't, right? It won't work because in the process of backpropagation over the window size, if you see here, output depended on input T with an activation and the state. So here, output T depends on state T minus 1 with an activation there. State T minus 1 itself depended on state T minus 2. State T minus 2 depended on T minus 3, and all of them depended on the first input, right? These are a lot of functions, nested functions. Activation of, right? And then if you do the backpropagation, you need to do derivatives. I assume you know how backpropagation works. You need to do derivatives. And for that, you need to do a lot of chain rule. If you want to do derivative of a nested function, if you remember from calculus, right? Derivative of f of g of x is you need to do the chain rule. However, a lot of these multiplications are values less than 1. And if they are multiplied together, basically the whole gradient that we get from the backpropagation process would be close to 0. It won't cause any update in our weights because we update our weights based on the value of the gradient, right? So if the gradient is close to 0, nothing is updated in backpropagation, and the model can't learn properly. Because if you don't do updating backpropagation, how are you going to change the weights? And it makes it difficult for RNN to predict based on entries occurring at the start of long sequences, because there is no weight update for them. Did you get the problem? It's all fine? For example, here's an example why long-term dependency is needed. We call it long-term dependency. That's the term that you call it. Imagine it's again the text completion. I grew up in France, and then you talk about a bunch of things that you did in France. At some point, you say, I speak fluent. What is the word that you think would be the best completion there? French, right? However, if the sentence was so long and it did, and France was not in the window of the word there, the model could not predict it. So you have to increase the window size. And if you increase the window size, you have the vanishing gradient problem that the model couldn't learn properly. So anyways, an RNN can't solve this task if there is enough info in the middle. That's the problem that we have with RNNs. Any questions? All fine? You got the problem? Any questions on Zoom? Okay. So with that said, let's see what, okay, researchers were like, oh, we have this problem, RNNs are so good, but we have this problem, we need to somehow figure this out. And they indeed figured it out. First, they started by finding some ways to mitigate this problem. By mitigate, I mean they didn't solve it, but they added some tricks to RNNs that tried to solve it. Today, we will see those. Tomorrow, we will see another approach that they did to fix this problem for real. Almost fix this problem. And the second approach was that led to now like GPT and these kind of models that if you pass a book to them, a long book, and you ask a question from somewhere in that book or somewhere in that slide, it can find it out because it can handle long-term dependencies very well. RNNs can't. The approaches that we will see today are only tries to help RNNs. They didn't solve this problem, so keep that in mind. Let's see what they did, what researchers did, because these are the things that we need to know before getting to what we will see tomorrow that will solve this problem. So this was an RNN again. We had input, hidden, input, hidden, input, hidden, right? This is like a very simplified architecture. And this was practically how it worked. So it was the input, it gave the previous state, and the input, it moved through a tangent hyperbolic whatever function, and it gave an output, which was both the output and the next hidden state, right? So it would both be the output, and then it would also be passed to the next RNN. This was how RNN worked. Now we will see another architecture, which is called LSTMs. You will see, wow, how complex is it? Let's see how it works. Oh, sorry. Let's see how this works. This was a try to help RNNs handle long-term dependencies better. Let's see. Here we have the input, right? Let's put this string. Here we have the input. The input has two different functions here. That sign is the sigmoid. Sigmoid is the one that you keep between 0 and 1, right? And the tangent hyperbolic is also. If you pass it through sigmoid, actually, tangent hyperbolic also gives you a range, right? We usually use sigmoid for probabilities, but it doesn't mean that you should always use sigmoid for probabilities. That's just one example. But here we don't care. Here we have 4 different functions, and we have one line. So here you see the previous state, right? But you will see 2 of them. So each cell now gives us 2 outputs, which are calculated based on a function of, again, the current input and the 2 outputs of the previous cell. The idea is that we have some stuff here, the multiplication, the addition. We call them gates, and the idea of these gates is to control how much info comes from the input, how much info comes from the previous state. It was a question that one of you asked. Could we control how much we use the current input and how much we use the previous state? I think one of you asked this question. And the idea is that, yeah, LSTM is a solution to that. So we can control how much we attend to the previous state, how much we attend to the current input. If for a task we need more long-term dependency, we adjust the weights in a sense that we can attend to the state more than the current, and so on. Let's see different components of the LSTM in action, and then we will go on writing some code to see impact. The first thing here that we have, okay, I know change this. I actually got this graphics from this website. It's very nice. This is the same diagram, but we just highlight top part. One of the parts here, that's the top part, is the cell state. Cell state is a line that is running in the whole chain. You see? From the first cell to the last cell. We call it cell state. The cell state means that the info can flow even without changes. Why? Because if the output here is 1 and the output here is 0, basically C of t would be equal to C of t minus 1. So you can adjust the weight in a way that always the cell state can just go. However, it also allows us to be able to add or remove data to the cell state. You can add data here. If it's negative, it will be removed, or we can also multiply it by a certain amount to make it bigger or smaller. Basically, here we have the output of sigmoid. Here, right? You know that output of sigmoid is between 0 and 1, right? If it is 0, C of t minus 1 would be multiplied by 0. What would be the output? 0. So it means that let nothing go. Forget everything that you learned. So what it would do is that it would forget everything of the previous state and it would just attend to the current state. If the output of sigmoid is 1, it means that it would multiply by 1, which means that let everything go. And if the value between 0 and 1, it would downplay the effect of C of t minus 1. The less it is, the less we keep from the previous state. Any questions? First from you. Yes.
So can I make the statement that the LSTM works better than the RNN?
Again, depends on task. In many tasks, yes. Normally, they would. So the thing is, even in short window sizes, we sometimes see improvements. Like, yeah. But you can find tasks that RNN might work better than LSTM, or they might not be significantly different. It's not a proven mathematical rule, as I said, it's just empirical evaluation. But in practice, they work better than RNN. However, they have downsides that I will get to.
But the LSTM will use more computational.
Yes, basically. That's the main downside, yeah. And you're also more difficult to implement, which is like something, but yeah. More difficult to implement, but you can use libraries, it's fine, but more computational because you see a lot of things are being computed here, right? All of this is like more computation. Yeah. But normally they work better. But we had to introduce RNN first so that you know why this was built in this way, right? So that's what and also when you see tomorrow transformers, also no one uses even very few people still use LSTM. There are still tasks that LSTMs are near state of the art or very good, but normally people would still use transformers or neural models. But yeah. Peter, maybe go to the chat.
So one question was why the gates will send information and give needed information to the hidden layers. But I guess the question is more or less how the gate understands which information to preserve.
The idea is that all of these are weights that are trained by backpropagation. So when you train the whole thing on the data, basically the whole backpropagation process magically, interestingly, manages all these weights in a way that the model will work. So we don't adjust them manually. I mean, you can also adjust them manually in theory, right? But in reality, we let the model train from the time series itself to be able to find all the values that are needed in different set, all the weights.
Second question, what is the CT and how is it different from HT? And I guess related one is why CT won't forget information, the HT will forget information. That's why
it's not that CT won't forget information. CT can also forget, but it can control how it forgets.
So
Here.
I guess maybe why CT is a long memory and HT is a short memory.
Okay, yeah, that's a very good point. Because you can say, yeah, HT also depends on HT minus 1, right? And there's a valid, totally valid command. The thing is, H of T is not from an output of directly a sigmoid layer, but an output of sigmoid and tangent layers multiplied and summed by C of T minus 1. You can say, but it's the same thing, and that's true. These are metaphors that we use. When we say there is one line, it doesn't mean that it's really a hardware thing, that is we have connected one wire and we add multiplication and division, right? It's just a metaphorical thing. These are all just basic mathematical formula, but we do this metaphor, at least researchers did this metaphor, to be able to come up with these concepts, and then in practice they saw that it works. It doesn't mean that C of T is in nature different from H of T. I mean, correct me if you're wrong, but that's the thing, right? These are all basic mathematical functions in the end. C of T is CT minus 1 times sigmoid of X of T plus H of T minus 1, blah, blah, plus, right? So it's just a mathematical function, but we frame it in this way so that's easier to understand. And more intuitive for the researchers that came up with this. One of the ideas is that you see how researchers came up with ideas so that in future you might be able to come up with new ideas as ML researchers, as deep learning researchers. They saw how previous people came up with ideas and they came up with this. So it's useful to always see their thought process. Before getting to there, any online?
So could you explain again the idea why do we use several gates?
Yeah, so basically here, I mean, you will also see the other gates and what they work, but here the idea of this gate is to control the flow of information from CT minus 1 to C of T. Again, the output of this is a sigmoid, so it's between 0 and 1. It could let all of the CT minus 1 go through or none of it go through. It's basically, gate is again a metaphor. It's not a real gate. It's just a multiplication in code, but basically a multiplication is a kind of mathematical function that can control how much C of T depends on C of T minus 1. Yes. I think you had a question? You. No one? I thought someone raised.
Why CT save more information than HT? They have the same length.
It's not saving more information. We don't make this claim. No, both of them are a kind of hidden state. We call it the cell state, but it doesn't mean that it saves more information. It can save more information if the output of this layer is 1, for example. But it doesn't mean that no, it necessarily saves more information. It's just a mathematical formula in the end.
So CT is long-term memory and HT is short-term memory, and sigmoid function allows us to manage the impact of the long-term memory by multiplying it.
If you use those metaphors, yes. If you want to use metaphors, you can always think like that, yeah.
Actually, like if I could say at the comment, I would say like, we have an interpretation that this works like this, and based on this interpretation, we implement architecture that should work like this.
Exactly.
It may work like this, it may not.
Exactly, because in the end, they are mathematical formula. The model does not really know, oh, this is long-term memory, so I should return information in my long-term. They're not humans. These are dumb models. This is just mathematical formula. So in practice, we say long-term, short-term, but it might not train properly. But yeah, I think that was a good example, exactly. So in reality, this is just a mathematical formulation, but this is just interpretation, a metaphor, a kind of thinking that helps us think about that. All fine? So let's consider the things that we have here one by one. So we saw this part, right? We saw the top part, this C of t minus 1 to C of t. Now let's go forward. We have another thing, we should call it a forget gate. Again, we want to ask why a forget gate, because it's just another mathematical function, but okay, people call it a forget gate. What does it do? Get the previous h of t minus 1, gets the current input, passes through a sigmoid, and outputs. So it's basically this. It's a weighted sum of the hidden layer and the input. This W is just a weight matrix, right? It's a weighted sum of this, plus a bias, of course, and you pass it through a sigmoid. The idea is that, why we call it a forget gate? Again, this is just a naming that researchers love to use. You can call it parser gate or like whatever, right? It really doesn't matter what you call it, but they call it the forget gate because the output is multiplied by C of t minus 1. So if the output is 0, it leads to C, this line, forget the previous information because it multiplied by 0. That's what we call it the forget gate. And the metaphor that you can use to remember is that you use it to forget information after a new subject in a sentence. For example, you are reading, you are training RNN on a text. And for example, it's a bunch of short stories. And whenever each short story begins, says once upon a time, blah, blah, you want to forget information. So you can, the model can learn that when it sees once upon a time, it will adjust the weight in a sense that it would give a 0 in the forget gate. So it will forget the previous information. You can think of it like this. The model might not necessarily do this. Actually, one thing that you will see is that explainability of those models are very difficult. Like you can't get an LSTM and see on the value and see, oh, see, the model learned this here, forgot this there. It doesn't work like that. These are just metaphors for us, and basically they are mathematical for us. Another gate is the input gate, which specifies what new information are we going to store in the set of states, metaphorically again. So we have this I of t, which is calculated in a very similar way to f of t. It's like a sigma of a weighted sum of h and current input plus bias. And then we again do another weighted sum of the h and x, right? Of the h and the current input plus again a bias, but this time we give it to usually tangent hyperbolic. You might say, why here a sigmoid, there a tangent hyperbolic? Who knows? They did it, it works. So we just keep using it. That's how many things work in deep learning, unfortunately. And then they are here multiplied together, right? So we just calculate I of t and c tilde of t. Then to form the new cell state, you multiply C of t minus 1 times f of t, as you can see here. Then we add the output to the multiplication of I of t and c tilde of t, as you can see here. So the new C of t would be equal to f of t times c of t minus 1 plus I of t times c tilde of t. And you know that how all of them are calculated. You don't need to basically know the mathematical functions. You don't actually even need to know this because now there are libraries that implement this for you unless you want to do some low level stuff and so. Fine. Any questions? Yes.
So maybe if you come back to the previous slides, so what is the meaning of adding xt and ht minus 1 going to the same node?
So these are the two. So basically, it's similar to the normal RNN that you had, right? Each neuron got the current input and the previous state. Here, by this formulation that they have here, why it doesn't show? Oh, here. Here, by this formulation, it means that this is a weighted sum of this. So with weights, like it gives some weight to the current input, some weight to the previous state, and it sums them together. It's like a weighted average or weighted sum or whatever you want to call it. So it's basically a matrix, like you can consider it as a matrix multiplication kind of thing, right? In practice. So that it depends on not only the current input, but also the previous HFT. All right. Anything on chat? Okay. We also saw how the new self is from, right? Perfect. Then we go, okay, finally, how this output is constructed. Until now, you might have thought that until now, we don't know how to use CFT. Like we are just updating CFT, where it is used. Because if you're just calculating CFT, it's why do we care? We should use CFT at some stage, right? And that's what we do here. So in order to calculate the H of T, it depends on three things. Depends on previous H of T, depends on current input, and also depends on C of T. Let's see how it is calculated. First, we calculated O of T. It's again similar to how we calculated F of T and I of T. We call it the output gate because it's used to calculate the output price. O of T is a sigmoid of it doesn't work. It's a sigmoid of a weighted sum or weighted average of the current input and the previous state plus bias again, and then we multiply it by the tangent hyperbolic of C of T. That's what they saw it works in practice. So yeah, here. This was the line that we had, and we have a branch here, tangent H, and then multiply them together, which we are expression. It just basically that formula, it's not fancier. They just saw that this would work. Like it's when you look at it, it's very random. Why tangent H here? Why they do this, that, there? Based on every combination that they tried, this worked. It's not very rigid mathematically, but it works. Any questions? I mean, there's not much question here really because it's like it worked. So, I mean, we can't question it really, but was it clear or fine? Yes.
I guess it's like a summarization. So if I get some previous information with sigmoid, then save some new information with 10, and our model learns weights in distribution between 0 and 1 to just forget or have new information.
The weight is not necessarily between 0 and 1, by the way. Like the W is matrix of values. It does not necessarily, I think, need to be between 0 and 1, right? But of course, the output of sigmoid is always between 0 and 1. Yeah.
And each step we update C, H, and after this get output. I guess yeah, we update them all together.
Yes, exactly. So at each state, we also get the H of T out, and we also get the C of T out, which are both used in the next state, right? C of T is only used in the last step to calculate H of T, but H of T is used for almost all of them. So H of T is more involved. C of T is something that is touched less. H of T is something that is more involved. That's usually the basics, right? Okay, so before getting to that, this was one way of helping RMS. There is also another way, which is gated recurrent units. This is a bit simpler way. Basically, just another way that works in practice. They merge the cell state and hidden state. This was one of the questions that you also asked. Why do we have two of them, long term and short term? No, we can have only one. And then they also combine the forget and forgotten input gates into an update gate. Let's see how they work. Diagram might be a bit more complex because they have less number of states, so they have to combine everything together in a very fancy way. We calculate two things from the input with a sigmoid. One of them is Z of T, a weighted sum of H of T minus 1 and the current input given to a sigmoid. And we also have R of T, which is again a weighted sum given to a sigmoid. Then we have a more interesting thing. We multiply this R of T by the previous state, and we conduct a weighted sum of this with the current input, and then we pass through a tangent. Okay, we'll say, what the hell are you saying, Partha? And yes, it's just the way that it works. And finally, we will have an update value that we will partly use that and partly use the previous H in order to find the H. You can see here, right? H of T is equal to Z of T times the new H of T plus 1 minus Z of T times the old H of T. So if Z of T is close to 1, Z of T is the output of sigmoid, right? So it's basically 0 and 1. If Z of T is close to 1, this term will be 0. So it will basically forget the previous state. And if Z of T is close to 0, this term will be 0, so it would just retain the previous state, and it would not learn anything. So by moving z of t between 0 and 1, the model learns if it should attend to the new information or it should continue retaining old information. And all of these weights, WZ and WR and this W, are all learned in the backpropagation process. So if the RNN LSTM, if the LSTM or GRU see a lot of training data, they would find weights that would work this whole process for all of the data, and hopefully would work also for any new data that we will give to the models. Yes.
C of T a lunch parameter, or it's like handcrafted?
None of them are handcrafted. All of them are based on W. Whenever you see W, those are the weights that are learned in backpropagation.
Oh.
Yes. I mean, in theory, you can also modify them yourself, right? In theory, you can do anything, but in practice, they are learned from backpropagation. Anything that is at the big W, both here and also here. You see, for example, here we have a big W. Here we don't. Here we have two big Ws, right? And here another one. These are all learned in the backpropagation. So you don't care what are those values. You initialize them to random values. You give all of that to the model, and then based on input output, it will learn the backpropagation. Peter, online questions?
How does GRU solve the problem of having to increase the window while avoiding addition rate?
It doesn't solve the problem, as also LSTM didn't solve the problem. The idea is that these tricks help the model to be able to map h of t to the previous h of t minus 1 using fewer operations that do not necessarily depend a lot on tangent h and sigmoid, but can depend a lot on plus and multiplication. And those functions do not need necessarily chain rules, as we had chain rules there. So we will have the vanishing gradient problem less. But it doesn't mean that we don't have that problem. It's just a way that helps models to be able to continue long sequences without needing to necessarily go through tangent h at every step. Here, the model, if they want, they can have weights that does not depend a lot on the tangent h and depend mostly on the previous state. So in theory, it can be a bit better regarding vanishing gradient, but not 100%. I hope that answered it. Any questions? So basically, yeah, we have the reset gate that changes the hidden state, and update gate where we can metaphorically say it's for the long-term memory. So to recap, LSTMs and GRUs can help mitigate the vanishing gradient problem, but only mitigate it, not solve it. And they're also useful for text that we will cover a bit today and a bit next week. There is one main concern about this, that they are not very interpretable. You can't, for example, look at here and see the value of weight here and see, oh, so this means that the model has learned this or that. It doesn't mean anything like that. They are not interpretable, which is a negative aspect. We will see some stuff about interpretability also later. And then also, these models are not used in practice that much these days. People use transformers, but because transformers build upon the concepts that we learned today, we needed to go through them. But in practice, you do not necessarily, when you have a new time series, you don't necessarily start with an LSTM, always. So that's something to know. Yes?
I'd ask you to repeat what's R and Z for GRU.
Sorry?
What is R and Z for GRU?
Oh, here. Here. So basically, these are just values that we define. R and Z are both defined the same way. A weighted average or sum of the previous state and the current input has to anticipate, but the weights are different, basically. And then they are used in two different places in calculating h of c. They're just two different values based on two different weights. I mean, from a mathematical point of view, they're just two different values, two different functions with the same inputs, basically. Maybe you can frame it like that.
Is vanishing gradient mainly caused by chain rule with stamp, or sigmoid also bad for vanishing gradient?
Any kind of function, like any kind of nonlinear function, I'll make you use the chain rule, right? I'm not wrong, right? Yeah.
But ReLU is not so bad for the chain rule.
That's true.
The problem with sigmoid stank is that the norm of your
That's true. It's still ReLU is nonlinear, right? So it's still nonlinear. That's literally the only reason that we have ReLU is to make it, because if our whole network is linear, it won't learn, right? It's proven that network should have non-linearity in order to be able to learn in backpropagation.
No, it should be. It should have non-activations to be.
Yes, the activation should be non-linear.
In order to learn non-linear functions.
Yeah, of course, non-linear function. But in practice, our functions might not be linear, right? So if you wanted to learn anything, it should be non-linear.
Yeah, but the question is about vanishing gradient. And
Yes.
I guess vanishing gradient is only because we are doing repetitive stuff, and if the norm of our gradient is less than 1,
Exactly.
we have vanishing gradient. That's
Exactly. Because a lot of less than 1 are multiplied each other. And it would be close to 0.
for sigmoid and tank, it's less than 1. For ReLU, it's not necessarily less.
Not necessarily, yes.
So,
I mean, yeah.
so it's mainly because of tank and
Yeah, I think generally that answer is true. Yes. Yeah.
when to choose LSTM and when to choose GRU.
Depends on the task. I don't think there's a rule. Like, I think still up to before transformers, a lot of papers that came out compared LSTMs and GRUs. I've seen those papers. Like you see old papers, they just apply both methods or like several models and just compare them. Similar to how now people compare different transformer-based models. At that time, they compared different RNN-based models. I don't think there's a certain rule. If you know anything, let me know. But I don't think there's like very.
I would say people choose LSTM when they want more interpretability.
I think both of them are not interpretable in that sense, right?
Long-term memory thing is more clear in LSTM than GRU, but LSTM is much slower.
Yes.
Than GRU, while achieving the same performance most of the time. So
Yes.
Mostly prefer GRU.
That's true, yeah. About interpretability, I would still say, okay, none of them are really interpretable, right? So these kind of deep networks all have problems with interpretability. We can't necessarily say they're but what you say is also true, yeah, because I mean, we can say, I don't know, trend towards interpretability, maybe we can frame it like that, yeah.
So why GRU reduces vanishing gradient if it's uses a lot of sigmoids and terms?
Still, I think this is similar to the first question that was asked, right? It can pay less attention to those. And as a result, basically the weights of these that come here could be 0. So h of t can retain information from h of t minus 1 without necessarily relying on those functions. So in practice, the weight of those that is applied in the chain rule when you do like a plus in the different terms could be 0, so that in practice, those 0 gradients do not have much effect, but still, this is something that is in practice, not proved in mathematics, as far as I know. In practice, it mitigates the vanishing gradient compared to us. Compared to RNN, sorry.
Is there any task where RNN is better than transform?
Yes. Sorry? Could be. For example, I know, one specific task. Actually, the task that I did, we will code today. There was this paper that I think showed that if we just do bare bones transformer, bare bones LSTM works better. And also, usually I think RNNs have less memory requirements, so that's also something. It's not that always transformer is better, but I think the default these days to use transformers, really, I would say. Yeah. Because, I mean, we'll see tomorrow, it's not too far from now. So yeah, okay, with that said, maybe we can go to coding. We'll try to finish 8:30 maximum, I hope, or even before. And we'll move one part that we have to tomorrow's lecture, so no worries about that. Let's see, this part is coding basically. We want to code an example. We will code a real case study, which is called the student knowledge tracing. Students, this is a real case study of time series. In a real learning system, for example, Moodle, or like Coursera, edX, like whatever these kind of online tools that you use, right? A student interacts over time and answer questions. For example, imagine there's an assignment, is a massive online open course, like this kind of open courses that you can enroll online to answer assignments. A student answer questions of a certain topics, right or wrong. Just take the very simple case. Each question is a multiple choice, you get it right or wrong. For example, here you see there are a bunch of questions. Each of them come from a certain skill. For example, in the course of programming, could be knowing functions, knowing arrays, knowing pointers. each of these skills is a skill of one question, and then the students answer them right or wrong. So do you agree with me that it's a time series? Time series, right? These are a set of questions, the kind of time series, and answer right or wrong. And then we want to see if we can predict their answers to the next questions or not. Why is this useful? In a real world system, is useful because you can know which question they are more likely to answer, for example, wrong, so that if you want to train the students, you can show those questions to them. You can show questions that they will likely answer wrong, so that they can learn from it. Because the idea is that you design adaptive quizzes that people can learn from it. This has been actually a very long topic of research. Is part of also what I do research day to day in my lab. This is actually a figure from my own paper. But yeah, so we are working with this simple task. We are trying to design an RNN model to be able to predict this. So we will code it together. As you see, the data is pretty simple. As I said, researchers have explored different ways, Bayesian models, Markov models, a lot of these ways to predict the mastery of each skill. This was this professor, Chris P.S. from Stanford, first time in 2015, showed that, yeah, you can achieve a state of the art at the time results with just using an LSTM. And we are trying to write what he did in his paper now. Let's see. So let's get to it. So we have a data set here that we can just import. So it's KT data / I'm using, of course, the cheat sheet that I have on my phone for the file names and all of that. Train.json.
That's the LauzHack, it's not sensitive.
No, it's fine. It's fine. It's just this directory of everything here. I can close it. It's like my LauzHack deep learning summer bootcamp, so it's fine. Yes. Train.json as a file. Data equals json.load. I think we need to import JSON as well, right? And then I want to convert it to a data frame. I assume you know all of these, right? Data frame JSON. I assume you know Python, but if you have any questions, you can just ask. And df train could be the data frame data. And then let's print it to C. So this is the kind of data that we have. We have different students, the questions that they answered, the answers, and the difficulties. Difficulty is a number from 0 to 2, because some questions are more difficult than some questions. And also if they use the int or not, but this is not very good in this data set, so we are not going to use that color. But we are going to have all the questions and difficulties and predict the next answer. That's what we want to do now. Did you get the task? It's like very pretty simple. I chose to pretty simple so that we can demo it, right? Let's also load the test data the same way. Test.json, right? And then df test. Df test. Perfect. All right. Then let's import this data set in Torch, as you assume you already saw in the previous 2 lectures, and then try to work with it. First, we need to prepare it as a Torch data set. That's a PyTorch data set that would allow us to save all of the question of the answers and difficulties as arrays. Yes.
What is the target? What we want to?
The answer to the last question in the window. So here the windows are of size 5. You see, 5 questions, 5 answers. We want to predict the 5th one based on the previous 4. So it's a window in capacity, basically. Yeah. Yes. So let's do it.
Excuse me. The answer 1 and 0. There are just like there is a binary answer system like true or false, or it's like it's correct or not.
No. One means yes. It's like binary about a student's correct or not. If answer is 1, it means that the student answered correctly.
Yeah. Okay,
0 means it wrongly. Yes. It doesn't mean that like you selected true or false. These are actually not even true or false. These are multiple choice questions, I think, in the real data set that it was collected from. 1 means they answered correctly. Yeah. Perfect. Class or data set which inherits from data sets. I need to import data sets. Maybe also data loader. I just accept the suggestions of Copilot. It almost said the whole thing, but let's write it in a way that I can tell you what exactly are we writing. So we are writing the initializer of this class. We want to get the data frame in the input. And then what I always try to do to have sequences and labels. Sequences are inputs and labels are outputs that we need to predict, right? We usually call them labels because it's like a classification task. We have labels. Here's a kind of classification because we are classifying if the next answer would be also correct or wrong, right? So we can also call it a label. Then we iterate over the data frame. So the answer of this data frame is the raw answer, and the difficulty is raw difficulty. Difficulties or difficulty? Difficulties. You see Copilot something wrong. Right? So we just get them from here. Answers, difficulties. Right.
Answers.
And answers, true. Thank you. You see Copilot is always wrong. So yeah. I was also strict. So answer difficulties. And then we want to add to our sequence the tuples, basically the tuples of answer and difficulties. So what I do is that I define the sequence as an empty array, and then for I in range of len of ans minus 1, I will add to the sequence. Why do you think I only added -1? Let's reject this thing. How can I reject it? Yeah. Why do you think I only added to len of ans -1 and not to len of ans? Because we didn't want the last, right? We want to predict the last here. So we want to have basically here we have 5 of them. We want to have the first 4 and predict the last, right? So we only here add to the sequence up to len -1. Because otherwise, if it sees the last, it will always try to predict the last value, right? It doesn't make sense. Fine? Until it was fine? Sorry if I'm going a bit fast, but I hope it's fine. Then we add it to the sequences. Then we add to the labels, we don't need the difficulty, the last answer. Here also it's better to make it arrays because always better to work with arrays in PyTorch. So what I did here is that these sequences that I made, I appended to the whole array of sequences that I had, and then I added the last answer. -1 in Python means the last value of the array. I added last at what it should predict. So basically, it will get as input all of the time series of answers and difficulties, and will predict the last answer for me. Any questions here? Fine.
Could you please repeat how is this time series will change if we change answers order?
Sorry, you repeat.
Why is it a time series? What will change if we change the answers order?
In a real world environment, so in this data set, when you answer the question, they see the correct answer and they go to next. So they learn over time. So if, for example, they see a difficult question first and then they see an easy question, it might be easier for them to answer that question compared to when they see the easy question first and then see the difficult question. In basically this domain, this type of, we call it knowledge tracing because we are tracing the knowledge of a student. This is known that the order is important. So in practice, in this task, the order, in the way that this data set was collected, the order was really important. Also in a real exam, if you do the answers in order differently, you might achieve different results, right? If you don't have the chance to get back, the order would affect your results. So basically that's what you understand. Any questions? All right. So yeah, again, here sequences is an array of arrays. You see, each of them is an array that is like added to this, right? Sequences is an array of arrays, and each array would be answer and difficulty. And then labels is just one value. So we have array of arrays, which is like array of answers, and then you get the final answer and label. Usually for the data set, you also need to define, as Copilot suggests, the len, which is very simple, len of sequences. And then you should also define the get item. These are the items that you usually always define in Torch data sets. I don't know if you have seen it, but otherwise, 3 methods: initialization, len, and get item. Get item means I want to receive the tensor of that specific item, so it will give to me. And it's very easy. So x is torch dot tensor I will just autocomplete it because that's what I wanted. So X is our input, right? Our input is the tensor of the sequence at the current ID. And also the type is float 32 because we always use that for our models. And then also we do the same for Y, but with labels. And then we return X and Y. Any questions here? This was just the boilerplate code that you always have when it comes to PyTorch. Have you seen this len and get items before, Peter? Okay, so you already know this. It's pretty good. Okay. So this is our data, how do you call it? Data set, right? I call it our data set literally. Yes.
Self.labels.append s -1. This is just to initialize predictable value with anything. Can you repeat why do we do this?
No, this is not the predict. This is the final label that you want to predict. Like this is the last answer. Answer of -1. If answer is like 1 0 0 1 0, answer of -1 is the last 0 in the end. So we want to predict that. In our sequences, we don't have answer -1, as you might see. We only have the previous answers. So we are using this to predict the last answer, basically. Yeah. Yeah. All fine? Good. Let's then define the model. Class, I will call it again our model because for some reason I will love the word all. Torch.n and our module. This is exactly how we define the torch model, as I've assumed we have already seen. Self init, self, super dot init. Okay, good. Then you define the RNN layer that you want. Self.rnn is equal to torch.nn.rnn. Input size. So there are several things that we can set. One of them is input size. Input size is 2. What does it mean? The comment that Copilot itself made. Each sequence element had 2 features, answer and difficulty. So our input size, basically the size of our vector at each input is 2, right? Because as you saw here, this list has 2 values. So basically our input size here would be 2. If we had more features, we would have increased the input size here. Then we have the hidden size. For example, 32, 64, or whatever, right? Size of the hidden state. Of course. Yes.
Do we know the difficulty of the last question?
No, here I didn't. The idea is that we want to predict, no, in general, would they answer? Yeah, that's true. We can also add the difficulty of the last question. It depends on the specific task. In some tasks, you want to just predict if a new question would come, do they answer it right or wrong as a heuristic for their mastery of their skill. That's what we want to do here. You can also pass the last difficulty, which is another thing. But yeah, what you said is practically true. In my current code, I don't pass the difficulty of last question. Okay, we can have some layers. These are just hyperparameters, right? There's nothing fancy here, really, to be honest. And then also we usually say batch first true, which makes it the input shape in the shape that we want, always batch equivalent features. I assume you have already seen these. And that's it. What the hell is trying to do? Okay. And then in the end, we also, so this is our RNN. We usually also pass a quick linear layer on top so that we can get the output. So we say self dot ending layer, hidden size was 32, yeah, and then torch and linear 32 and 1. This is basically the output layer. Because why do we need this? The hidden size is 32, right? So in the end, it gives us an output of size 32. We want one value, 0 or 1. So we convert it basically in a linear format to 1 dimension. Any questions here? All fine? We just convert it to one layer so that we know, yes.
Just quickly remind, what is the hidden state?
Is the dimension, is the size of the vector of the hidden state, basically. So hidden state was this. What's the thing that is moved here? Like the here. The vector that is here has a size, right? The size here is 32. The size actually should be big enough. There is not only one number, because one number is not expressive enough to store information. It should be big enough, but then we should in the end convert the last one to a single number because we want to get a single number. So we add an ending layer, which is like a linear layer. Yes. Maybe you.
We have done this and end sequential that we did yesterday.
What do you do yesterday?
We say that we can do another special like.
Oh yes, you can. What I want to do is to call them step by step in forward. So it may be useful if you saw sequential. This is another way that you can do it. You define them independently, and then you will call all of them in the forward layer. But I will not write it. But before that,
Is there a computational reason why we use powers of 2 for the size?
I think in reality, not anymore, right? Good point. I never thought of this. Sure, you know? Why do we use 3264? Is there really computational reason or just we are used to it?
So first of all, less people are errors. Secondly, GPU is optimized for something.
Is it really optimized if it's 32?
Something which is divisible by 8.
Oh, just divisible by 8. It's not powers of 2 necessarily. For example, 48 would also work. I see. I didn't know that actually. Good point. I'll check it out. Yeah, I didn't know. But I think the custom is to always use powers of 2, like 32, 64. I think. At least it's the custom because, yeah, programmers love powers of 2, you know? Yeah. So then, okay, this is another. So I think you saw the sequential way before. This is another way. Good that I read this way so that you also see it. You define the forward function in which you first call the RNN. Actually, let's have it. And then you call the ending layer. So what does this mean? The code that Copilot completed for me. You see that you no longer need to memorize code. Copilot can write it. So as long as we just understand how the code works, it's fine. But also remember that Copilot can make mistakes if it gets a bit complicated, so you need to understand it properly. So what you do here, first, we get an X in input. This is the forward pass basically, right? We call the RNN that we defined here. Perfect. Then we pass it through ending layer. But why we pass this weird thing? This literally means that take only the last output. So this second parameter is the sequence length, right? The -1 there means that only take the last output and only pass the last output through the linear layer because we want to only get the output here, the last output, right? We want to only get the last output. Why we don't get an output from the beginning, from the middle? Because, for example, X2 has not seen the inputs that come after X2. So in order to do classification on the whole time series, we should always get the last output. Fine? Any questions here? Why do we need always the last output? Oh, fine. So here we get the last output and then we return. It's perfect. Now let's do the training. Let me run this still, by the way. Run, no compiler, good. Train data set is our data set. We have trained, we just defined it, right? And then we define the data loader. I assume you have already seen it, right? You have seen data loader, right? Data loader into perfect. So basically, this is the boilerplate code that we always have, right? Then I define our model. Then you define the loss function. For example, you can use. So what loss function do you think we can use here? It's a classification task in a sense. So we can use, for example, cross entropy. They have seen loss functions, right?
I talked about cross entropy and then.
Okay, yeah. So basically here we are using the cross entropy, right? The BCE. And then we can have an optimizer. I assume you have seen Adam. I just accepted whatever learning rate it suggested to me. I think 0.001 is good. Should be fine. So let's run it. Good, perfect. So now we have our model, we have our loss function, we have our optimizer. Let's now run the training loop. I think 20 should be fine. Yeah. Let's run for 20 epochs. I remember, I think from in the last iteration of bootcamp, we run for 20 epochs and it was fine. So let's do it. So we first go to the training mode. This would tell the model that it needs to offset the gradients, right? So we go to training mode. Then we store the total loss because I want to print the loss for you to see that how the loss decreases over time. Then we I want to go step by step. Copilot, stop. Okay. So don't look at the code because I want to go step by step to explain it. So for X batch, Y batch in train loader, we basically go over the batches that the train loader is giving to us. Each time we do the zero grad. I assume we have already seen why we do zero grad and how it works. Then I usually love to call it Y pred. I'm so used to it. This means basically the predictions that we get as low output that are different from the real Y batch. So Y pred is just model of X batch. So we just give the input to the model and ask it to provide the output at the current epoch. At the beginning, of course, the model tells random stuff, right? But over time, over epochs, the model would learn. Then we just run the loss function. We have to do the squeeze for the dimensions to work. And then loss function is basically between the prediction and the batch. It would tell us that what's the current loss at this epoch. We do the backward pass. We run the optimizer. And we add this to the total loss basically so that I can print it. And then I will just accept whatever it tells me. Epoch. Loss is total loss divided by length of train loader. Any questions here? I think it's a pretty, yes.
Do we use RNN for this task in this example and not, for example, fully connected?
So it's the same time series, right? Yeah. It's a time series. So, okay, this is a pretty simple task. So maybe even a normal model would work. I chose a very simple task, only 5 windows, so that we can train it very easily in like 10 seconds. Of course, in real world, you do not have these kind of tasks, right? You have more complex tasks. But we wanted to, so it's a tutorial, right? It's a kind of tutorial instruction so that you see, yeah, it runs. And this is a time example of time series, so we want to use RNNs. I can also use LSTM or whatever. Fine. Okay, let's run it.
Why do we squeeze?
It's just for dimensions. Actually, I think this Y pred is because I think Y batch gives you just the Y output, but Y pred gives in the same dimension of X batch for each of them, and it will squeeze so that it would be the format of Y batch, right? You didn't say. So here, I also don't know how to describe it properly. So basically, the shapes are different, right? Maybe I can print the shapes.
This removes the imaginary dimensions.
Yes. Let me maybe print the shapes. Maybe that's a better idea. Print. So yeah, this is a good idea. So see here, when we print the Y pred shape is of 32 times 1. We don't need the 1. The 1 is just the 1 dimension, right? We want to just have 32 values. Here, as you can see, Y batch has these 32 values. So in order to make this, get rid of this 1, we just call a squeeze, which will basically convert it to a 32 dimension.
It will remove all bus from the shape.
Yes, it's removing all of these dummy dimensions that don't make sense to us. Include this one here, right? Clear? This is basically whenever you have mismatch, actually Copilot usually tells you to use a squeeze. You don't need to think about it. Now it automatically suggests me to use a squeeze to match the data shapes. But whenever you have this kind of mismatch, 32-1 and 32, you just do the squeeze to make them work. Questions? All fine? Okay, so let me make this break again. Restart the whole thing, run again, so that the model is retraining. Oh, no, I didn't want to print that. Sorry. Otherwise, it would be too much printed stuff. So you see here, the loss is decreasing. 62.5, 557, 551, 52, you see? But then after a while, it's not decreasing anymore. And it's actually a bit increasing. But also in the end, it's okay. It's after a while, the loss is not decreasing that much, but it's still good. I think it's not that much bad because it's not also increasing. But anyways, this decrease means that our model is trained, right? Of course, the loss doesn't get to 0. It means that maybe the data is so random that the model can learn properly from it. Now let's evaluate the model to get the accuracy. They have seen the accuracy metrics, right? F1 or
F1, no. Manual accuracy.
Manual accuracy. Okay, perfect. So let's see. Okay, let's load our test data set. Now we want to test our model on the test data set, right? So we've trained and trained, we want to test on test. Perfect. We turn on the eval mode, right? And then we make two values, all pred and all labels. These are basically the values that we can compare to find our accuracy. I now want to evaluate the model that we trained on the test data set. So we torch no grad, it means that don't upgrade the gradients. We just want to test the model. We don't want to train on any of these. We again do the same thing that Copilot is suggesting to me for X bash, Y bash into test loader. Cred R model X bash dot. We should also do the squeeze here. What does this do? It means that every time we again get the pred. These preds are not the true values. These are what our trained model said about our test data. You get it, right? So these are X batch and Y batch are from the test data. These are not the data that the model was trained on. So whenever we do this, these are preds that the model thinks are the real values for the X batch. Is that enough? We should all, if you print preds, these are values between whatever, like it can be whatever value, right? We want to have it between 0 and 1 so that we can do a prediction. And then, for example, say if it is more than 0.5, we evaluate it as 1. If it is less than 0.5, we evaluate it as 0. So basically, we pass it through a sigmoid. Wow, how did it know? So towards the sigmoid preds. Then all preds, yes.
What is the difference between model.eval and torch.grad?
I think one of them is actually fine, right?
No.
Really?
Model.eval.
I always rule at both. What's the difference? Maybe you know it better.
I don't know if you want to hear me. So model.eval only changes the way how inference of your model works. For example, there are some layers that operate differently during training and during evaluation, like dropout or batch down, something like this. But gradients are still calculated when you say model.eval. So model.eval is only to ensure that layers that behave differently will behave in the mode they're expected to be in. And with torch no grad, we ensure that the
gradients are not updated. Oh, that's a good point. I always did both. Actually, I think I answered this question wrongly in the previous bootcamp because one person asked me and I think I answered wrongly. Thank you. I didn't know that actually. Good, good. Yeah. So you append the pred and then also the labels. Here, labels are the true labels. Preds are what our trained model predicts. And we want to compare it against each other. Now the values are between 0 and 1. So if we print, for example, all pred.
So the question is loss here from 0 to 1 or it's not?
Oh, no. That's why we are passing through sigmoid. Now it is from 0 to 1.
It's out, but I mean the loss above.
No, not necessarily. No.
It seems pretty high, and I agree.
Yeah. I mean, it is high, yeah. I mean, this data is not very good. There's also only 5 examples. Even a human cannot learn anything from the data, right? So it's like a toy data set, but yeah. So you can see, if I print all preds, these are values. How can I get sense of these values? I need to convert them to a categorical variable, like 0 or 1. You can actually use a very good function for this in torch. All preds. Torch.cat, all preds. Cat is not cat or dog. Cat is categorized here. So when it's a torch.cat, it means that it would convert them between 0 and 1. And also I do it with all label. And then, for example, if I now print all pred, you will see that it's still not. Wait. What happened? Oh, sorry, this is not the categorization. I made a mistake. This is the concatenation. Oh my God. I'm so bad. Yeah. So basically this, yeah. So sorry, everyone. We do the categorization ourselves. That was another framework that we needed. We did cat for concatenating. Sorry. This is basically for concatenating this data in a format that gives us one list. Sorry, everyone. So, any questions here?
There was a question, why
Yes.
do we apply sigmoid?
To make it between 0 and 1, because we want to have as a probability, interpret as a probability, and then if it is more than 0.5, we say that's the correct answer. If it is less than 0.5, we say it's the wrong answer.
It's also maybe important to know that we are predicting the probability 1 plus, not as is a softmax case.
Yeah, exactly, because here it's just a binary, right? 0 or 1, correct or wrong, exactly. So then we need to convert this to a binary value. Maybe to float so that it's easier. Print predicted. What does this do is that whenever each value of all pairs is more than 0.5, it says a 1, and otherwise it says a 0. Okay? Any questions here? All fine? We just convert it to a binary value, right? Then let's calculate the accuracy. Now we have the predicted and all labels. Also, if you print all labels, is also another set of values. You see here, you can already see, for example, the first one was predicted incorrectly. The second one was predicted correctly. This one also correct, you mean? See? This one was predicted incorrectly, this one was correct, and this one was correct, right? So predicted are the ones that we predicted, and all labels are all of them. We also, by the way, try to finish in like less than 5 minutes, so that you can go. Any questions here until now? Fine. Then let's calculate the accuracy score. You can import accuracy score from the scalar function, and then accuracy is equal to accuracy score, all labels, and predicted. Oh, sorry. Good, right? We have an accuracy of 0.7374. That means our model has an accuracy of 0.7374 after 20 epochs of training. Good. Do you think there is any issue here? Like, do you think 0.73 is a good accuracy or not? What's your intuition? It's bad generally, yeah, because it's not close to 0.9, but also imagine that our data set was also pretty big. Like it was a toy data set. In a real world data set, you will have better results. I couldn't show you a real world data set because for that, sometimes you need to go through permission and a lot of this, right? This is a toy data set. I mean, it's also real world, but the simplified version. However, there is one big problem. Imagine you have, I don't know if that has been covered, so I will describe it. Imagine you have a data set in which 90% of labels are 1 and 10% are 0. If you predict something, just you predict 1 without any model, without any deep learning model, just you say 1, what would be your accuracy? 90%. So maybe here 73 is actually bad. Maybe our data set is also imbalanced, and actually it's something like this, that 73 is actually worse than random, worse than just predicting a majority. We should always ensure that we only calculate accuracy on data sets that are balanced. By balanced, we mean the number of entries in one class is almost similar to the number of entries in another class. If it was 50-50, of course it would make sense, because like 50% is the baseline, the accuracy is 0.73, so it's better than baseline. But here we can't say anything, and we don't know it until we check. So let's do it. Let's check the distribution of last answers. Last answers in the real data. Basically, this is what I wanted to print. And print last answers. So there are last answers, and then we can print value counts. Last answers dot value counts. Value counts is a function that will tell you how much of each value do you have in the data. What you see here? We have much more correct than incorrect. Not much more, not like this, but there is an imbalance. It means that in the data set, students tended to answer correctly than wrong. which can be true in a lot of data sets. Usually, when we have such imbalanced data, instead of using accuracy score, we should use other metrics. One of them that we can use is called balanced accuracy score. That would automatically improve, open this point for us. Let's calculate this. It's a very simple. Instead of accuracy, I wrote balanced accuracy score, right? Simple. And then you can see that it dropped. You see? It was 0.7 something, and now it's 0.6. This is the actual accuracy of the model. Because the other one, the model can just tend to say more ones than zeros, and that doesn't mean anything because we have more ones in the data set, so we'll have a higher accuracy. However, this would balance the effect out, and this would be closer to the real accuracy that the model has. So it always makes sure that if the data is imbalanced, that you can basically check, always go with balanced accuracy, but it's still good. Okay, not good. You shouldn't use this in a real world system and publish a paper out of it because this is not a very good, maybe not a very good balanced accuracy unless you want to show that your model does not work in a certain domain. But better than baseline. So at least it means that it's more than 0.5. So at least your model has worked. Any questions? Also online? Okay, so that's it. Let's quickly recap the code and then call it today. And then I'll do the other part that I wanted to do today tomorrow. So we imported the data. We created the data set. We ensured that our last answer does not get into the sequence. We defined our RNN input size 2. Input size 2 which means that we had the answer and difficulty as the inputs. Hidden size 32, whatever number you want to set. We put a number of layers, which is the hyperparameter. We should ensure that we convert this hidden layer that 32 only to one value because we need one value in the end. We define the data loader, we define optimizer, then we run it for 20 epochs. And we see that the loss is decreasing. Then we do model.eval and torch.nograd. That thanks to what Peter said, both of them are necessary. Then you iterate over the test loader. Each time you predict with the model, you pass it through sigmoid so that it's between 0 and 1. You concatenate all of them together. You convert it to a discrete value. If it's more than 0.5, you call it correct. Otherwise, you call it wrong. And then you compare the accuracy score. We found a normal accuracy score, not too good, not too bad. But we said that because of the data imbalance, it might be a problem. We checked, yes, we have a data imbalance. We have way more corrects than wrong. So we calculated balance accuracy to balance that effect out. Any questions? By the end of the session, you should. Yes.
Could you please repeat once more what do we use cat here for, like a bit higher than here?
Very exactly. Sorry.
Why do we use cat here? Just what does it do?
Oh, because the data, as you can see here, is a bunch of different arrays that you want to all to concatenate together into one big array.
Oh, I see. Thank you.
Yeah, sure. Yeah, I actually made a mistake initially, but that's what it is. So yeah, by the end of the session, we should know how to code a simple RNN from scratch on a given data. You should know the basic concept of the RNN and their limitations and LSTMs also. You can replace the whole thing with LSTM and test it. Tomorrow, you will see transformers, which is another architecture that came after RNNs, after LSTMs to fix also the vanishing gradient and some other problems. Transformers is now the basis of GPT and a lot of models that we use these days. And we'll also get a bit into natural language processing by getting over embeddings and some early information that you will need for next week. Yes. Yeah. That's I think I also have to because I think today we're already late.